Gj, which is the center of mass of link J. Okay, so right. So hopefully you can see that this right here is basically the same thing as that in kinematic coefficient land. And this next term, the angular kinetic energy, is this. This is simpler, right? Because it's a planar scenario there, and it just has one component coming out of the page there. And if you take the first order kinematic coefficient of theta and times it by the input variable, whether that's a rotation or a translation, it doesn't matter, right? That'll be the angular velocity, and that's what's squared. That's this guy. Okay, so hopefully you can see omega j squared is this from previous lectures. Okay, so that's kinematic coefficient land. And remember, if you do all your velocity analysis and do velocity analysis of a point, you can know these x and y gj prime, and from just traditional velocity analysis, you'll know theta j prime of each link j. Notice we're just finding the kinetic energy from this equation of one link j. Okay, if you want to find the total kinetic energy in the mechanism, you'd want to add, J1 plus J2 plus J3 and all the way through all the links. Okay, so the question then is, in the power equation, it's not just Tj, right? It's the derivative of t with respect to time. Okay, it's the derivative of that with respect to time. So what is that? Well, can you take the derivative of this? Okay, that's probably the hardest derivative you'll ever take in this class. And let me give you a hint. Okay, note that if you take the derivative of, say the x component, or it really doesn't matter if it's x or y, but let's say the x component of the, first order kinematic coefficient at point Gj on a link with respect to time, then just remember x prime Gj is dx Gj divided by d phi. So you can see here, we just basically wrote that out. We simplified that, wrote it out. We keep the first d, but there's another d that comes to us, so it's squared, and then here's the d phi in there. So hopefully you can see how that goes to there. Okay, and now you can use the chain rule basically and pull this out. Okay, or basically maybe think about it by timesing this whole thing by 1, and where d phi over d phi is 1, right? And so now you have two d phi's there, so it's squared, and you still have that same top, and then you take the dt out, and there's your other dt phi. All right, so you can see these would kind of cancel out, and that would equal that. But hopefully you can see that's the second order kinematic coefficient of that point, xgj double prime, and that's y or phi dot. Okay, so with that hint, I would put me on pause and try the challenge of taking the derivative of this, this part of the equation right there with respect to time. And you'll have to use the product rule and chain rule and all kinds of fancy things. And you'll definitely want to use this identity we just proved. Okay? So if you've done that or you didn't want to put me on pause, that's fine. I'm going to give you the answer here. Okay, so, all right, so if we take the derivative of this first, these are both changing with respect to time, and that's changing with respect to time, so you have to do the product rule. So you take 1/2 mj derivative of this times the normal one of that, and that's all this, okay, but then you take plus this again times the normal one of that times the derivative of that, which is all of this. So I'm going to first explain this. How do you take the derivative of this in there? Well, you kick the 2 down, you put this in, and then you take the derivative inside there with respect to time, which is all this. Okay, so you see that. Okay, you do the same thing on the other side, you get this, and then remember you take the normal one there. Okay, so if you got that, that's impressive. And then the other part of the product rule for this is all this same stuff, but now you're going to take the derivative of that. It's 2 phi dot, and then you have to take the derivative of the inside with respect to time, so it's phi double dot. Double derivative with respect to time. Okay, so if you got this, that's super impressive. But then you do the same thing over here. And again, it's product rule because these both change with respect to time. And so doing the first side of this is that, and the second side is that. Okay, you see this is the same as that, but this one's the derivative there. And this is with everything the same here, but you're taking the derivative of that, and you're using this except with theta j. Okay, where you're going to get theta j double prime phi dot from there. Okay, so there you go. Big messy equation, but that's the derivative. That's the change in kinetic energy in kinematic coefficient land. Okay, so if you reorganize this, take this equation, reorganize it, go ahead and put me on pause and make sure you agree that this simplifies to that. Then you're getting closer to the final grand equation. We're going to just change everything up here, but keep that the same. And I'm going to show this. And this basically is an equation. This is what you'd want to write on a cheat sheet or commit to memory that uses this. Okay, so notice this is just the change in kinetic energy with respect to time of link J. Okay, but this is the total thing in the power equation. This is up there. That's the change in kinetic energy with respect to time for all the links summed together. So that's why here we have these sigmas. And you might ask, well, why don't you start with J1? Well, because remember, link 1 is usually always ground. And for this case, it better be ground, right? Or this equation won't work. So there's not going to be any kinetic energy in link 1 if it's ground. It's not moving. So you don't waste your time calculating it. So start with J2 and go through N where there's N links. And then A is this component plugged in there times all these input things. Okay? In this case, the input, if it was omega 2, our favorite one, it would be omega 2 and alpha 2. And that would be omega 2 cubed, where this is all B. Okay, and just hopefully you can see that all this stuff comes from that equation here that you derived. Okay, but you'd want to package it like this. Okay, and note, if you do velocity and acceleration analysis, you'll have all the theta primes and double primes, and you'll have all the x, gj primes and double primes of every link if you do the velocity and acceleration of a point. All right. So this is the cheat sheet. You write this down and sum all the change in kinetic energy in there in the power equation. You've got it. Okay? Great. So that's boxed. All right, so now let's move on to the change in potential energy with respect to time. Okay, and remember there's two ways we have potential energy, at least in mechanisms, two typical ways. There's the gravitational potential energy, okay, and you have to consider that for every link. So that's U, gr for gravity, and J is for the link. Okay, so you take the mass of that link times G times that Y from some datum is the displacement from some, or not the displacement, but the distance from some datum to the center of mass, Gj on the link. And but if you take the derivative of this with respect to time, remember it's the derivative, then you're basically going to get mg, mj, g times the derivative of y, or the speed that's changing from the datum, and the speed is just simply y gj, assuming y is in the, if your coordinate system is x and y, and gravity is going the y direction, it's the first order kinetic coefficient y prime times phi dot. That's the definition of velocity of y of point G, which is the center of mass in the y direction, right? Okay, and again, we're going to start with link 2 because link 1 is never going to change. There's never any velocity there. It's never going to go up and down in the gravitational field because it's the ground, right? So you just start with 2, and there you've got it. And you go through all n links. All right. All right, so that's how you find that. So that's pretty easy to sum all those gravitational potential energies up from each link, from 2 to n. Now let's look at springs. Say there's say E is like an index telling you what number of the spring is. Well, say you had Q springs, okay? If you take the derivative of this potential energy with respect to time, you'd see you kick the 2 down, that would cancel. You'd plug this in and take the derivative of that. So it's Ke delta delta E prime, first order kinematic coefficient, times phi dot, and those things times each other is going to be right, the velocity of how much that spring is deforming. Okay, so so very good. So and this is a distance. This is essentially the velocity. All right, and again we have to add those all up for every spring. Here we do start at 1 because no spring will ever be ground. It's an element that deforms, and there's a length that's the ground. So we start where E is 1, and we assume there's Q springs. So if there's 3 springs, it goes 1, 2, 3, and you add them all up. Okay. Okay, so that's how you, and then of course you add these two together. Once you've added all this, and you've added all this, you add these two together, and you get this. Of course you can add energy, and of course then you can add power together, which is what we're doing here. So that's you'd want to take, that's the equation you want to write on a cheat sheet, knowing these things. I mean, actually, you probably, this is obvious that you add these, but you probably want to write these down. Okay? All right. So now, finally, we're going to do the dissipation, the power due to dissipation. Okay? Recall that remember, there's the 2 sources of dissipation that were probably going to be relevant for a dashpot, or sorry, for a mechanism, which is your mechanism may have a dashpot attached to it, or there may be friction in the joints or on a sliding surface of a slider crank or something. And you want to find that power, okay, of dissipation to heat. Okay, and so remember, here's the equation I sent before, but D is now the index of, how many joints how many dashpots there are on the system. And if you divide this by delta T, now it's the derivative here, divide that by delta T, this equation here divided by delta T, see that drd divided by delta T is going to be rd dot. So you basically have CD RD dot squared. Okay, and so that's why, of course, RD prime times phi dot, that's RD dot, right, that's RD dot. That's really confusing to say. So RD prime times phi dot is RD dot, right? You know that. And so if it's RD dot squared up here, then that's just both of these things squared. Okay, and again, the index is D, and we start at 1 because, of course, no dashpot's going to be ground. You start at 1, and in this case, say there's R dashpots. So say there's 4 of them. You add them all from 1 to 4. Okay? Okay, and then finally, there's dissipative energy of sliding or joints. This is probably more common in reality. There's few mechanisms actually attached to a dashpot, but you might model them being attached to a dashpot. But pretty much every mechanism has friction in the joints or on the slider sliding on something. So you'd want to know this one, okay? And remember, that's the equation. That's either the static or the kinetic coefficient of friction. You'll know if the mechanism is moving or is static. Which one to use will be, and that's the normal force, then dr, right? So you divide both sides by delta T because it's a derivative here. And now when you divide this by delta T, we get, that's the derivative RT, so that would be RT dot, which is essentially RT prime times phi dot, right? You know that from first order kinematic coefficient lecture. And so that's pretty simple how this turns into that. But again, the index here is T, and there's S, joints or things sliding. Okay, so, and again, none of them would be ground, so you start at 1 and you add them all up, all the sources of friction. All right, and then of course you add those two together. So this is obvious. You probably don't need to write that on a cheat sheet, but you probably would want to write these two equations so you don't have to rederive them, although they're pretty easy to derive. Okay, and you definitely want to understand those derivations. All right, so let's do some examples. This is the most important part, so let's talk about it. All right, let's just read this. So again, we have our favorite 4-bar, and say in the 4-bar mechanism shown below, or actually to the right, maybe would have been a better way to write it. a couple M4 acts on the follower link 4. Okay? Determine the couple M2 acting on the input link 2 in order to see the input link rotating at a constant counterclockwise, that CCW rate of W2. Okay, so the situation is, it's like, you know, you've got a moment on both. We give you M4. That's the moment on M4, and you're trying to find what is the moment M2 that you put on 2, so that as this thing is moving, that link 2 is rotating at a constant angular velocity counterclockwise of omega 2. Okay, and you know, oftentimes you don't know what direction to draw these moments, you know, these red arrows here in this convention. So you just always draw them positive, and the signs will always end up working out. Okay? Okay, assume that the link centers of mass are at the midpoints of the link. So, you know, unless they tell you the links have different density distributions, and you need to like somehow find the centers of mass, then you know you'd have to do that, and that would be complex. But if they don't tell you that, you can just assume the links are all the same density, and the centers of mass are in their centers there for these rectangular links. Okay, and they're labeled G3 and G4, and well, they should be labeled G2. There's the circle there. Okay. All right. Okay. Also, assume that the mechanism moves in a horizontal plane. Okay, that means gravity acts perpendicular to the plane of motion. So usually we like to think of gravity pulling down, but what they're saying is gravity in this case is going out toward you. So you'd have to think of the mechanism like this, and you rotate it down, and it's working in this plane where gravity's pulling down like this. Okay, and the reason they say that is because right then since it's a planar mechanism, nothing's going to lift up or down in the field of gravity. So the potential you know, energy due to gravity is going to be 0, whereas it wouldn't be if the gravity was acting down in this direction for that thing. So, okay, for that orientation. So for this example, they're basically telling you gravity is coming out of the page at you, or into the page. It doesn't matter. Okay. Assume position, velocity, and acceleration analysis have been performed, and all kinetic coefficients are known, which is good because if they're not done, then you have to do them all. Okay. So, you know, like I said, exams in this course are pretty brutal. If you get the vector loop wrong, you could get everything wrong. Velocity analysis, acceleration analysis, and power equation, just totally wrong. So it's important that you do that vector loop right, and hopefully you can see now how critical it is to understand that lecture, because everything builds on it itself here. Okay, so let's find it. Let's find that moment using the power equation here that keeps you know, link 2 rotating a constant omega 2. All right. So first of all, okay. Well, let's see. I already told you the gravitational potential energy change is going to be 0 because gravity is acting out of the page and nothing's lifting up or falling down. You know, you don't have to hold up the weight of gravity. So it's no matter how much it moves, it's never going to change. Okay, so the gravitational potential energy is 0. And also, there's no springs in this scenario. Nothing's deforming. These are rigid links just connected by pins. So both sources of potential energy go to 0. So you can just, first thing you do is cancel that out. Okay. All right. Also, if they don't say there's friction at the joints for these things, you can just assume the friction at the joints is 0. Assume they're smooth joints. Okay. And so say there's no frictional dissipation, but what do you see a dashpot in there? No, there's no dashpot. It's not connected to any syringe or anything, or any plunger, and there's no liquid it's immersed in or anything. So you can also say this is 0. Okay, but you know this isn't 0, the change in kinetic energy, because the thing's moving, right? You want to find when that link 2 is going to constant omega 2. So even though you cancel these other two out, you have this. Okay, so you definitely have power because you have two external forces, or sorry, loads, moments more specifically, M2 and M4, and you know you have this motion one. But we've simplified it dramatically already. So let's find the power ones. Okay, the power one is m2 times omega 2 plus m4 times omega 4. Those are the two external loads, in this case moments, and those are the angular velocities of the links on which they're acting. And so you'd add them together. Now, again, convert everything to kinematic coefficient land. The input variable phi in this case would be theta 2 or omega 2 or alpha 2, right? Those are that's the input variable. Well, I guess the input variable phi is just theta 2, and phi dot would be omega 2, and phi double dot, would be alpha 2. So let's write in kinematic coefficient land where you do this. You see omega 2 pulls out here, and then theta 4 prime, first order kinematic coefficient of link 4, you can see times omega 2 would be omega 4. Okay, so you pull that out, and you've got it. Okay, so that's the power. That's the left side of the equation. So let's look at the right side of the equation, delta t. You'd write this on your exam, okay, from your cheat sheet. Hopefully you wouldn't have to derive this in the exam. You'd want to have this handy. And you'd look at it, and you'd start saying, okay, well, we want to find the situation where omega 2 is moving at a constant counterclockwise rate of omega 2. Well, if it's going constant rate of omega 2, then that means alpha 2 is what? Well, 0. If you take the derivative of something constant, it's 0. So this whole thing cancels out. So thank heavens, don't go solving all these first order kinematic coefficients and everything of A, even though you'd of course have to for B, but you can just ignore this entire term because it all goes away. Okay? And even you're adding these together, link 2, 3, 4, but they're all times by the input variable, and that input by the way, alpha 3 and alpha 4 may not be 0, but alpha 2 is 0, and because that's what they wanted you to get. They want to find the moment that gets that. And so even if you're looking at link 3 and 4 here, adding them up, this is still times that, and that's still 0. So this just goes away. All right? Okay, so then what you do is you keep what's left. You take this from the power, set it equal to this, okay, where B is that. Okay? And you want to find the moment. So what you'd want to do is, you want to find that moment. So divide omega 2 by both sides. This will go away, and that goes down to 2. And then you subtract this, and you find here's the moment m2 that would cause link 2 to rotate with a constant omega 2 velocity. Okay? And you would have already from velocity, position, velocity, acceleration analysis, know all these first order kinematic coefficients in B, and you'd know this one too. Okay? And remember, don't forget to sum them 2 through 4. Okay? And then you can solve that. All right. Okay, so now let's look at this example. This one's very instructive. Okay? So say we have a counterclockwise couple that acts on the input link 2 of the mechanism shown below. Okay? Notice, by the way, this is basically, might as well be behaving like a gear because it says no slip here. Or basically like a rack and a pinion, where the rack is ground. They colored it gray in this convention. It means it's fixed, held fixed. But there's no slipping, there's only rolling. Okay? So a counterclockwise couple acts on the input of link 2. They show it as M2. If the mechanism is at rest in the position shown, determine the angular acceleration of the input link. Now you might say, well, wait a minute. How can something be at rest? Like rest means it doesn't have velocity. It's not moving, right? But can something not be moving but have an acceleration? And the answer is yes, right? Like it's not terribly intuitive, but if you take a ball and you throw it up, right? There's a point where you're not touching it or anything, but gravity is constantly accelerating it downward with an acceleration of g, right? 9.8 meters per second, and that's why it decelerates. But then it reaches its apex, its top point, where the velocity is 0 and it is at rest. But then right after that instant, it starts accelerating the other direction and falls to the floor. So if you catch it at these instants where the velocity is 0, it's still accurate to say the object is at rest at that instant, but that doesn't mean its acceleration is 0. Its acceleration in the case that I just gave you is still g. Okay, so they're saying if the mechanism is at rest in this position shown, that means all the velocities are 0. Let's find the angular acceleration of the input link. So they want to find alpha 2 is what they're asking. Okay, the spring acting at the center of link 4 is always horizontal. Okay, which is how it's drawn there. And at the instant shown, it is compressed by a known amount delta. So remember, that's like if it began at L naught and it's now length L at that instant, it's L minus L naught is what delta is. Okay. The mechanism acts in a vertical plane with gravity acting downward in the plane of the motion. So this time they're telling you gravity is down. Okay, so it's pulling down. All right. So to lift link 2 and 3, you're going to have to move those against gravity, against the field of gravity, and put extra energy into lifting those. Okay. All right. So let's solve this. Let's solve this. Let's find alpha 2. Where these are at rest given some m2. Okay? All right, so here's the power equation. Let's go through it and find out what cancels. Okay, first of all, does this first term... Well, first of all, power doesn't cancel because we do have an input external load, which is the moment m2. So this doesn't go to 0. Does the change in kinetic energy with respect to time go to 0? Well, no, because even though, well, first of all, you might say yes because it's at rest. Okay, you might say, well, it's at rest, and so omega 2 is by definition 0, and therefore omega 3 is 0, and omega 4 is 0, and everything's at rest, and so there, if kinetic energy is the energy of motion, then it's 0. Well, you'd be wrong. Kinetic energy takes acceleration into account as well. Notice, that ball seems to very much be moving, except, that one instant it comes to rest. It's still accelerating. And you'll see, look back at that kinetic energy equation, and you'll find there's an alpha 2 in there as well, right? So acceleration, can have... can give something some change in kinetic energy, as you will see, okay, from the equation here. So, but don't just think because it's at rest this drops away, okay, unless it's like literally maintains a static structure that's not ever moving, okay. But if it's just one instant that everything happens to 0 velocity, the kinetic energy, the change in it is not 0, okay. Okay, and then we know this one doesn't drop away because we said gravity's acting down, and we're going to have to, things are changing either down or up in gravity depending on how the mechanism moves. So that doesn't go to 0. And also, by the way, there's a spring that's storing energy, so that's definitely going to be in there. But is there? Can we at least cancel the last term? Is there a dashpot in here? No, we don't see any dashpot. Is there any friction? Well, again, you always assume pin joints, maybe you assume there are roller joints in there, something with very low friction, and you assume they're smooth. And then, but you say, if this thing did rolling and sliding, the wheel there, if it was rolling and sliding, the sliding would definitely generate friction, unless it said it was a smooth surface it's sliding on. But in this case, they say there's no slip. It's rolling, which you can assume is not generating friction. Okay. Now, of course, if this really is a rack and a pinion and it's got teeth, even though the joint is counted as a J1, it's 1 degree of freedom. It's rolling only because you don't shear off the teeth. Though, that as they go through their mesh, from points C to P, it's actually sliding. The teeth are sliding, and from P to D, they're also sliding. It's only at point P, the pitch point, that there's pure rolling. So in reality, you may actually have to take friction into account, even though it says there's no slip here, if this is a rack and pinion with teeth. Okay, but anyway, that's just harkening back to our last lecture. But okay, for now, we're going to say we don't have to take it into account. We're going to idealize this. There's no friction. Okay. So we dropped that. So now let's find the power. Okay, well, there's only one load, so it's m2 times omega 2. Okay, and now you might be tempted to say, well, we want to find omega 2 when it's 0.